Okay, hello everybody. Welcome to this Foresight Aerospace episode. We will wait for some minutes for participants to join, and then we will start at 11 o'clock in 1-2 minutes. Okay, so fantastic. I can see that we have touched 80. I'm sure we will be much more. So again, hello everybody and welcome to this Foresight Aerospace episode. I'm very excited to see you all here today and to make an interesting session on challenges and benefits of hardware-in-the-loop simulation for aerospace and more electric aircraft. My name is SOHEIL JAFARI. I'm an assistant professor in gas turbine control and thermal management in the Center for Propulsion Engineering at Cranfield University. I will be moderating this episode for the next 90 minutes to explore the latest innovation within HIL simulation hardware and software for the design, analysis, development, and certification capabilities to deliver competitive high-value systems for current and emerging aerospace markets. First of all, I want to thank the OPAL-RT that kindly supports this episode and gives us the opportunity to have this practical and fruitful session. We have YAHIA from OPAL-RT today. We will listen to him again in the 20-minute talk. I also want to thank Foresight Aerospace for organizing this amazing episode. I'm a fan of Foresight Aerospace, by the way, and I have learned a lot from their previous episodes. And of course, a special thanks to you all for participating to this episode. I'm sure we will gain a lot from our discussions today. Well, about the agenda, after my brief introduction, we will continue with a 50-minute panel discussion with high-profile experts from industry. In our panel discussion, we will go through 5 main topics regarding the concept of HIL, current and future challenges, potential solutions, and the future roadmap of this high-potential concept. After that, we will listen to YAHIA BOUZID, as I said, from OPAL-RT. YAHIA has a very informative story for us on hardware-in-the-loop test benches for advanced and more electric aerospace. Then we will close the session with the audience Q&A, question and answer, where we will try to accommodate the attendees' questions as much as possible, obviously respect to the time limit. To help us in this regard, can I kindly request the attendees to put their questions in the Q&A feature in the screen so that people can vote for their favorite questions, and it will be very helpful for us to select some of them for the Q&A session. Thank you very much in advance for that. Just to mention that the webinar is recorded, and then you will have the link if you want to go through it again or share with your colleagues. So let's get started with a brief introduction on hardware in the loop simulation. HIL simulation provides an effective platform by adding the complexity of the plant under control to the test platform. The complexity of the plant under control is included in test and development by adding a mathematical representation of all related dynamic systems. These mathematical representations are referred to as the plant simulation. The embedded system to be tested interacts with this plant simulation. The HIL simulation will include electrical emulation of sensors and actuators. These electrical emulations act as the interface between the plant simulation and the embedded system on the test. The value of each electrically emulated sensor is controlled by the plant simulation and is read by the embedded system on the test as feedback. Likewise, the embedded system on the test implements its control algorithm by outputting actuator control signals. So changes in the control signals results in changes to variable values in the plant simulation. Consequently, from aerospace perspective, hardware in the loop or HIL simulation can effectively evaluate the reliability of the overall aircraft system. HIL simulation is characterized by the operation of the real component in connection with real-time simulated components. The simulated components are often the processes being controlled and or sensors and actuators. In particular, the framework can be used to examine the performance of aircraft systems, subsystems, and equipment such as, let's say, flight control system, camera hardware, fuel cell power, electro-hydraulic actuators, and of course, engine fuel control systems. So in our panel discussion now, we will explore the topic more with our experts. As the first step, let me grab this opportunity to welcome our respected panel members. To be honest, if I want to introduce them in detail, it takes ages to go through their expertise and shining background. So it's better to ask them to kindly introduce themselves very quickly. Today, we have YAHIA BOUZID, the Technical Director of OPAL-RT Europe. We have David Shaw, Non-Executive Director from Britten-Norman. We have Chris ELSEY, Digital System Engineer in Vertical Aerospace. We have Andrew Raw, UK Chief Engineer in Ampaire. And we expected to have SEYED MOHSENI, the CEO of the Samad Power, but unfortunately he had some emergency, so the absence is unfortunate for us. So may I ask the panel to introduce themselves, please, very quickly. YAHIA.
Good morning, everyone. And again, thank you for attending this exciting session today. So my name is YAHIA BOUZID. I'm Technical Director at OPAL-RT Europe. So I'm in charge of all technical activities of the company across Europe, Africa, and as well a couple of Eastern Europe countries, including Russia. I have a team of 5 engineers, and we are dealing with all topics related to tech support, to training courses, and pre-sales activities, just to make sure that the products and services that we deliver related to HIL test benches are properly used by our customers and that they are happy with them. And yeah, I would like to thank everyone here today, Foresight Aerospace, all the panelists, and SOHEIL as well for thank you as well for managing this panel discussion as well. And yeah, just wishing you to enjoy this session.
Many thanks indeed, Yahya. David Shaw.
Good morning. My name is David Shaw, and I'm the non-executive director of Britten-Norman. Most recently, I've been 14 years as a technical director there. And through succession planning, we're moving into new territories for me. My background is engineering. I'm a chartered engineer, fellow of the Royal Aeronautical Society. And I've been in the industry for over 40 years for various OEMs, simulator companies actually as well. Been at Britten-Norman, like I said, for 14, 15 years now. And we've been building, designing aircraft for over 60 years, and they're still flying all around the world. We've produced around about 1,300, and around about 700 or 800 are still flying today. And for all the new activities that are ongoing today, and I'm sure we'll touch on some of these topics, the island is a great product for testing and developing where we're all heading with electric engines and electric aircraft. Thank you.
Thank you so much, David. Andrew.
Thank you, SOHEIL. Yeah, good morning, everyone. I'm Andrew Ray. I'm UK engineer for Ampaire. I started my career at Farnborough with the Royal Aircraft Establishment and spent 20 years there in the aerodynamics department, working on design for Airbus, Boeing and Formula One teams, plus flight testing and certification. I jumped to academia 10 years ago and professor of engineering at the University of the Highlands and Islands in Scotland. And then I joined Ampaire just before Christmas to look after their UK activities as part of the Future Flight Challenge, which includes flight testing in the Orkney Islands and then down in Cornwall. Thank you.
Very many thanks, Andrew. Chris.
Good morning, everyone. Yeah, my name's Chris ELSEY. I'm the senior systems engineer within the digital systems team at Vertical Aerospace. So me and my team, we're responsible for the flight control systems, the cockpit systems, and the data and comm systems, and that includes all the kind of systems, hardware, and software. So a lot of complexity there. My background is Airbus, so I spent almost 10 years designing high integrity braking and steering control systems at Airbus for the A350-900 and -1000 aircraft. So I've got experience kind of certifying braking hardware and braking steering software for those aircraft.
Many thanks indeed, Chris. So now the participant will confirm that how difficult it was for me if I wanted to introduce these guys. So let's start the panel discussion. I kindly ask all panel members to participate in every question because the time is limited for 15 minutes. But I will start with a question, but let's have a roundtable discussion. So Yahya, in a few words, what is the HIL simulation?
Okay, so HIL stands for hardware in the loop, which is, let's say, a set of methods, techniques, and tools that can help engineers and engineering companies in almost any possible field in industry to validate complex control systems. So as we know, we have more and more software that is embedded in our complex systems. Can be cars, can be aircraft, can be any possible electromechanical device. And because we have more and more software that is embedded, it gets harder and harder to validate all these things because combinations are just crazy. So hardware in the loop is, let's say, it's an approach that can help these engineers, researchers to validate in a safer way and in a more effective way such complex controls before going real and before trying to test on real prototypes.
Thank you so much. If anybody else wants to add anything about a very simplified definition for the audience? Good, so it was a perfect definition. Yeah, many thanks. So, David, what are the main technological challenges based on your experience and what you have done so far? What are the main technological challenges related to innovative aerospace projects related to the HIL simulation?
I think the key for me is the system architecture. We're moving into sort of new territory, and this is where I can see the HIL could play a role. it's going to have to be developed. The airworthiness requirements are going to be following. So there's going to be lots of sort of work around that. It's not impossible to get things certified without the requirements. There's a process to do that. But the more that we can, tackle the system architecture and put a robust sort of reliability proposal together to the authorities, the easier it's going to be to get these things approved ultimately.
So do you think the system architecture is the key challenge in this topic?
Yes, I think so. I mean, obviously we're all familiar with the sort of way the aircraft works at the moment with a sort of fuel system. But what about the battery backups? What about the other system architecture issues we need to look at and work through?
Yeah, exactly. I know that Andrew in Ampaire, that you are strongly for many years you are working on electric aircraft or more electric aircraft. In terms of using hardware in the loop for more electric or all electric aircraft, what kind of challenges are you facing with?
I think it's a function of the fact that we're either taking new products or products used in different sectors into a different environment. So it's accommodating a control system that can firstly detect, but also then cope with failure modes that haven't become apparent beforehand. So if you take an automotive type battery and put it in an airplane, things will go wrong with it that don't happen in a car. So it's having a resilient system that can, well, firstly, try it out on the ground so it doesn't happen in the air, but then also be clever enough to recognize things and react in an appropriate way.
Yeah, you mentioned about the control system and failure modes. It was very, very interesting for me. What we are doing in Cranfield, working on different industrial projects, and we are developing several sets of HIL simulation. Recently, we have concluded that the main issue in embedding the control system in the HIL is the role of the real-time modeling. Because sometimes if I have a model that could be able to use in a real-time feature or in a kind of onboard control, it would be a game changer for design and development of the control and later on for the certification. Have you done anything in Ampaire regarding the real-time modeling for the new advanced systems that you are developing?
I mean, that's the crux of our HIL activity. It's real time, getting as close to the real world scenario as we possibly can before we put it on the airplane and fly it. I mean, you hit the nail on the head there with the word certification. I mean, it's all driven by that. Although the certification, as David mentioned, isn't fit for purpose really at the moment around electric propulsion or in hydrogen indeed. But how do we maintain confidence and satisfy that the necessary safety requirements within a certificatory process when we have new products that are more complex to fault predict and fault recognize within an already complex system?
Yeah, exactly. Thank you so much. Chris, what do you think about the current and future challenges?
Well, first of all, I'd just like to say a little bit about our hardware in the loop benches we have at Vertical Aerospace. So actually on our website, you will see there's kind of two benches that we've publicized. One of them being the system test bench. So that's this one here in the background. So that's an early picture of that bench that's kind of developed now. And that is for bringing on all of our kind of complex systems. So testing those systems in a safe environment before putting them on the aircraft. And we're designing an electric VTOL aircraft, and we're seeing there's a lot of kind of complexity around those systems. So we're finding that we are able to remove many problems on that bench. So that's been really valuable for us. The number of interfaces on there is huge. So the likelihood of seeing a problem is likely, but we're maturing the design early before putting it on the aircraft and able to do those kind of failure tests things that you can't simulate on the aircraft, and making sure we have the correct behavior from our flight controllers, for example, but also other controllers on the aircraft. So we use many emulators on that bench as well. So we have to emulate all of our sensors. We have a model for our aircraft, which is modeling the flight physics and dynamics of the other plants, and really testing our control systems and the interaction between them. So it's been used as an integration bench. The other platform worth mentioning is our pilot in the loop simulator. So this is where we have models of our flight control laws and flight control system, but interfacing directly with the pilot with real controls, real displays and switches. So we're able to run through different scenarios with the pilot, looking at different handling qualities and things like that, and failure scenarios in a safe environment, and starting to get that feedback from the pilot. And again, there's really valuable feedback that we are making design changes based on those that feedback from kind of test pilots and the test team. So they've been really valuable for us. So challenges really are the increased level of complexity. We actually can't have a fully representative sensor model running on a bench because it can't run real time. We can't go to the level of simulating atoms, for example, within our sensors. There's a balance to take between kind of latency and working in that real-time environment and the complexity of the model. So we have to really assess where are we getting value, and that model, sensor model, for example, would be used on a system test bench, but also on the pilot in loop simulator. And there's different variants of that model with different levels of detail. So it's a real challenge actually getting that level of complexity right and getting the value out of the testing.
Very interesting, the increasing level of complexity. Yet this is the thing that I think we can discuss a bit more details. YAHIA, do you want to add something?
Well, yes, I just wanted to react to a couple of comments I heard here. Thank you guys for your contributions here. So obviously, systems are getting more and more complex, that's for sure. Electrifying aircrafts, that's something that is quite challenging, and not only because it's not new, but we don't have yet many aircraft that are capable to have a full electric propulsion, for example. But electrification is a big topic today, and we shall not forget that we have many constraints that we have in aircraft that we don't have in systems which are just sitting on the land. For example, the weight, that's something very important. So the batteries cannot be super huge. So all the conversion systems, electrical conversion systems, which they have to fit somehow inside the aircraft, and that's a big deal in the end. Something I heard as well that I wanted to talk about was the what we're trying to test in the end, because we have let's say the expected behavior, the normal behavior of a system, which of course has to be assessed and verified and checked that in normal conditions our system is behaving as expected. But we have as well all the unexpected things that we need to take care of before the first flight. And this is, a way more complex topic because we know what the system is supposed to do, and we know what sets of inputs make sense, but we shall take care of the unexpected ones, or the ones that either would make no sense, or lack of information. How would our control systems behave if they are receiving inconsistent information? What happens if I have a combination of inputs which might lead to some strange behavior? And we don't want these things to happen while we're flying. So that would be as well one of the challenges to take care of, is how are we managing all this test coverage? How are we making sure that we are evaluating on the ground, let's say, all normal conditions and as well as many abnormal conditions as possible, to make sure that everything remains safe when we fly?
Yeah, that's a very, very interesting point. Yeah, many thanks. Yeah, it's about the covering of all test conditions. It's somehow related to the design of experiments, but even more, just to be sure that we can predict as much as possible. Chris, based on your experience, do you have any insight on this?
Sorry, apologies. Insight on what?
The point that YAHIA raised, because I know based on what you have done in vertical aerospace, you have done lots of HIL simulation for different missions or something like that. The question is that how we can assure that we are covering all test conditions, or how we can predict as much as possible the real world scenarios for a mission.
Yes, good question. It is certainly a challenge. So it comes to the design phase, I would say. So understanding what your requirements are, making sure they're valid, but also the kind of safety assessments that support that. So we have safety assurance processes that we run through, and those assessments include things like functional hazards analysis, or FHA. So what happened is the design teams will develop their systems and develop their functions, and then a safety expert will go and assess those functions and assess how those functions could fail. And the validation of that is then performed on the system test bench, kind of validating that assessment of the functional failure was correct. And that's kind of the first iteration that can feed back into design if it doesn't quite behave as expected. So in that phase, we'd be looking at kind of the loss of certain functions or erroneous functions. And that's the sort of thing we can test on the bench, and then ensuring that the control systems kind of behave as expected during that. Could result in kind of loss of redundancy and things, but we still need to, if it's a critical function, for example, we still need to make sure the aircraft can fly after these erroneous cases or these loss of functions. And basically there's redundancy in a system to cope with that.
Perfect. Yeah, very interesting. David, you wanted to say something?
Yes, just to add to that, really, is that going back in a previous life where I did a lot of work on aircraft simulators, we found just having actual hardware in the loop tightened up the whole simulation itself. And that was a huge benefit to the program. And just another point, building on what Chris says, that even as the aircraft and systems get developed, there's still a role to play, because I've found previous examples where you're both designing the sort of architecture and the hardware from the same design schematics effectively, but sometimes the real aircraft can be wrong. I've seen that where the simulator is actually correct. So even as you progress through the design process, there's still a role to play up until the very end of the development process.
Yeah, I completely agree with that. It's so useful having these platforms to kind of troubleshoot problems we may find on the aircraft. And yeah, the flight test team could identify a problem and maybe pinpoint it to a particular system or piece of equipment, but then they can continue their flight test campaign with their limited operation, so that problem doesn't manifest on the aircraft, while the engineers back in the design office can really kind of dig into that problem on the bench and work out where that problem comes from. So really beneficial and efficient as well, that we can continue or potentially continue flight testing. It obviously depends on the problem, and then working in the background, kind of iterating that design to fix the problem.
Very, very interesting. Yeah.
Yeah, that's something very important. I hear a lot. I mean, many people think that these simulations and all these hard in the loop things are mainly used for design, but it's not true. They can be used during the whole life cycle of an aircraft. Of course, they are extensively used during design. That's for sure, because we need to see how things work before they fly, right? But obviously, they make sense. Once the aircraft is flying, they can still be used in case we want to reproduce some behavior that we have seen on flight, or in case we want to make some kind of smart maintenance on the aircraft. So if you want to maintain it in operational conditions, so a test bench can be used, for 20, 30 years after first flight. So it's not only a good tool for design, but as well, it can help as well somehow in the certification process. But for sure, it's used a lot in maintenance for either, try to correct something that was wrong and that was detected during the flight, but as well to update embedded software. So in another life, I used to work for I mean, directly in the aerospace industry specifically. And we were working on a program where we were updating embedded code that was written at the first place in the 70s. And that aircraft was still flying, but we were still updating the embedded software because they were adding functions, or because or any component that needed some extra software functions. And we were using these test benches that were designed 40 years ago, and they were still there. So for sure, this hardware in the loop stuff can help during the complete life cycle of an aircraft.
Very interesting story. Many thanks. Yeah, Andrew. Andrew, you're on mute, I think.
One of us was bound to do it at some point. I'm glad it was me first. On the premise that all models are wrong, but some of them are useful, they become more useful if you validate it or benchmark it with real-world data. So as Chris and YAHIA said, they don't stop being useful once the aircraft is up and flying. You could validate them with real-world data. But also, there are some challenges, like things like no fault found, where they are ghosts in the machine if you look at the operational side of things, but you can do quite a lot to investigate those on the ground in a much cheaper and safer way than you can by just relying on in-service data.
Yeah, it's a very valid point, Andrew. Thank you so much. I just wanted to ask you about that, Andrew. Based on your experience, you saw that we are discussing several challenges about HIL simulation: system architecture, control system, failure modes, certification issues, increasing the level of complexity, etc., etc. In your view, how does HIL simulation tackle these challenges?
Well, it gives you data to provide as evidence of a certification process. It's not, well, I think for more electric aircraft, certainly currently certification by analysis is a long way off. For mature products, that's probably closer. But it's never going to happen until we can categorically predict the safety of complex electrical systems, and that's where HIL can play its part. It's not the silver bullet, but it can provide part of the answer.
We have got hybrid electric vehicles, and we have lots of backgrounds in HIL simulation for hybrid electric vehicles. Do you think, is there any lesson learned that we can use from automotive and implement it in the aerospace feature, or these are two different stories in your view?
I think that there are certainly lessons have been learned, but I think some of the constraints, and some of them were mentioned earlier, weight and different environmental conditions, different vibration levels, these sorts of things all create an environment which the same product wouldn't see on an automotive product. So there are certainly lessons to be learned, both positive and negative, I have to say, that there are examples of best practice that we should follow, but also we shouldn't do some of the things that have been done previously. But yeah, that's certainly lessons to be learned.
Many thanks. David, how you deal with challenges in HIL simulation in Britten-Norman?
We don't, on our aircraft platform, in a strange way, we don't do a lot of simulation. The reason is the platform is relatively inexpensive to modify. And so therefore, in a strange way, it's actually easier for us to test the real aircraft than actually trying to create a simulation. Now, of course, as we're moving into new architecture, then that's a different sort of game altogether. So this is where it will have some sort of benefit to that process, and particularly as we talked about on the architecture. So that's where we'll head with the HIL.
Yeah, it very nice. It brings another question to me. Maybe I can ask YAHIA firstly about that, and then we can circulate the point of view. YAHIA, what kind of systems can be simulated in the framework of HIL setup? Because we have got different perspectives and viewpoints from the panel members. So now I think we can discuss that. Okay, what kind of systems are suitable for HIL simulation?
Okay, well, sky's the limit, as we say. Actually, from the aerospace perspective, we can take the subsystem point of view. Either I'm working on the engines, or I'm working on the the air system, or I'm working on whatever electromechanical device that is inside. So we are more on the subsystem or the system side. So that would be the job of the manufacturers to make sure that their systems and their control units dedicated to these specific systems are complying with the regulations. That's one thing. And then we have the, let's say, the complete view. So if we are looking in a wider way at a, an Airbus or Boeing or whoever is manufacturing complete aircrafts, where they need to have a complete look on the flying device, so the complete aircraft, without needing to go into details of every single subsystem. So we have to treat each subsystem with care. But then when we integrate all of them together, then we need to have the complete sight of the system. So what is nice about these hardware in the loop systems or hardware in the loop test benches is that you can, let's say, tackle all these levels of detail. So we can focus on a specific subsystem, and we want to make sure that the air system or the braking system or whatever onboard flight system is working properly, let's say in its own environment. But then at some point we need to have as well a set of tests, or we need to have an environment that is capable to test the complete thing together and have a more macroscopic view on the complete system. So we have, there are test benches which are really focusing on a very, very small subsystem on an aircraft, like just one component, like one motor or one electric motor, which is kind of, it's a very small thing. And then you have others which are representing the complete aircraft with all the flight dynamics. So you can use this HIL in any possible subsystem on an aircraft, as well as on the complete thing. But then you just need to make sure that you're combining all these tests together to have the best possible coverage in the entire project.
Thank you so much, Andrew.
Yeah, thank you. Just to add to that, in addition to the kind of component level hierarchy, there's also fidelity hierarchy, and in the same way that with other numerical simulation approaches, that there are different levels of fidelity that are appropriate at different stages of the design process. So you would use a simpler, quicker, but hopefully correct process within your conceptual design that would become higher fidelity as you move towards detailed design. So there really is horses for courses. So and one of the tricks is trying to match the appropriate level of complexity and fidelity with the stage of the process that you're at.
Yeah, it's very important as well, Andrew. Yeah, it's another aspect of the question that you perfectly covered. Chris, what's your view on that? Before going through your view, I just want to read an interesting comment from one of our audience about this question. Pedro says that we use HIL for electrical architecture evaluation, requirements development, early performance prediction, software testing, functional development, bug troubleshooting during vehicle testing, regression testing for production software, etc., etc. So it's another view on this question. And based on what YAHIA said and Andrew covered, what is your view on the question that what kind of system can be simulated in the framework of HIL simulation?
For us, I completely agree with all those kind of benefits that Petros raised. And for us, it's the functional side. So with the complexity of the aircraft, there's a huge number of functions. So we've really focused on that kind of functional development and the kind of system integration. We're finding it less beneficial to include kind of thermal models in that and kind of vibration models. They would add a huge amount of complexity to the benches. So we tend to do that kind of a separate analysis and use the kind of the benches for the more kind of functional analysis and that integration.
So it's very interesting, at least for me, Chris, because you said that you don't think the HIL simulation is not a good choice for thermal analysis. Is that correct?
It not integrated into the benches we have available. So it would be a different hardware in loop model to do that sort of analysis.
Is it because of the different response time, or just because it increases the level of complexity? It's the matter of synchronization, or I don't know, multi-rate HIL simulation that you need for this purpose, or it's just a matter of complexity?
I think it's more the complexity. So with the very complex systems, we need to take some smaller steps initially. So until we have mature kind of functions, very confident in those functions, if we start adding in the thermal behavior and the vibration environment too early, it can actually make it very more difficult to troubleshoot some of those functional problems, because it may be due to the vibrations. But once we've got that maturity in the functions, then starts to include the thermal behavior, I see some benefit in that.
I see. Now it's clear. Many thanks. David.
Yeah, so I think where there are novel features or new aspects of design, and of course the electric engines and electric architecture is going to be one of those. That's where the benefit I see of the simulation. Also, we're doing a project where we're looking to automate the Islander, effectively turn the Islander aircraft into a UAV, if you will. And that's where I can see the HIL would be of benefit, because we can do a lot of this sort of scenarios on the ground, particularly, and I think Chris mentioned this early on, where you can inject faults into the system. And that's an obvious key concern when you're automating things, where you're doing flying controls and everything else with runaways and things like that. So that's the classic where I think the HIL would come to its own.
I see. Yeah, you wanted to add something.
Yes, actually, it was about what Chris mentioned about this, some behavior or some models that might be simulated in different test benches, such as a thermal model or thermal behavior. We shall not forget let's say the base or the core of what real-time is, and what a hard loop test bench is. That is, have a setup where we have part of the sim that is real and part of it that is simulated. So why would we do that? Actually, the idea is that we want to test for example, some control system, and we want to lure this control system so that he somehow thinks he's sitting on a real aircraft, and we just want to make sure that he's behaving it is behaving as it would if it was in an aircraft. So we are more looking into the dynamic behavior of a complex system, such as an aircraft, when it comes to control different electromechanical devices inside. If we want to make a thermal analysis of a system, and if we want to see how the heat is impacting, the materials, or how mechanically, or what mechanical behavior we might have depending on the speed and all these things. So there are special tools for that, which are simulation tools, which are more offline. So we don't care that much about having a real-time behavior there. We can just leave a simulation running for days and see what happens in the end. Let's say the framework of the hardware in the loop test benches is that we want to study the dynamic behavior of a system. We have some real hardware that is sitting in the experiment, and we need to make sure that what we are simulating is being simulated with the right time constants so that we can properly lure that control system that we want to test. So obviously there are hundreds of tools that can help engineers to simulate systems with different perspectives. It can be mechanical, thermal, it can be hydraulic systems, so it can be so many different things. But obviously HIL or real-time HIL, that's just the subsection of these things, where we are focusing on the interactions between control systems and the electromechanical devices and sensors that they are talking to.
I would agree with you, Yahya. I would agree with this comment that, for thermal management system, we more or less are interested in a steady state behavior, or any kind of offline simulation would be more than enough at the moment. The only question of mine about this comment is that recently we are facing with some new concept like PTMS, power and thermal integrated power and thermal management system, in which we can see that for some specific missions where the maneuverability is important, the proposal is to have an integrated control systems for both fuel control and thermal management system. What would be the role of HIL in this concept, in your view?
Well, actually, it's a lot of question of what level of detail we can give to the models that we are running. Of course, we can integrate together different functions, and we can have systems which are doing more things at a time, or that are taking into account more complex interactions. That's just fine. But when we are modeling such systems, we might not need to go, to a level of detail that is too precise. For example, if I want to see, if my control systems is properly managing, let's say, thermal behavior, or if it's reacting properly to an overheat or whatever, I might not need to know what is let's say the heat dispersion on a surface. I don't need to have that level of detail. I just need to know that the environmental temperature is above a certain temperature, and that would be enough for me to trigger some fault, or to be in this kind of in this loop or in this other loop. So the question is, we cannot have models which are infinitely precise. That's super hard to get, and we can't have everything at the same time. There is no device in the world that can model every possible engineering domain and every possible level of detail. So we need to filter at some point. So there are tools that can allow to have this very detailed view of a thermal behavior or some kind of mechanical behavior on the system, so they can assess how it would react mechanically or thermally speaking. But then when it comes to the control part, you need to simplify things, and you need to take into account just some variables that would make sense, and any further detail in the modeling would not add significant value to the validity of your test. And that's the tricky part. So what is the model that is good enough for me to assess the system, but not too complex to keep it feasible in the end?
Yeah, exactly. As you said, it's a tricky part, and we want to find a generic solution for this question. That's exactly what we are working on these days at Cranfield. So let me somehow summarize something, because we have just 10 minutes. I'm really enjoying the discussion, but I have to add another question to this panel discussion. Andrew, we discussed the challenges and opportunities with the HIL, more or less based on our time. Finally, can HIL simulation totally replace real prototypes? And if it can, where?
I think I kind of covered this earlier, that at the moment, no, that there's not enough reliability in the process, or enough data to validate the process that we could with HIL. I think we're getting there with more mature sort of dinosaur burning tube with wings type designs, but with novel powertrains, that's not going to happen, in my view, in the near future.
Thank you so much. David, what's your view on that?
Yes, like Andrew says, really, there's a limit there. And I think there always is going to be a limit. Where I see the HIL is in that development function is the key, as far as I'm concerned. Because what we're trying to do is minimize the time spent in the air, perhaps, so we can uncover some of the larger problems, perhaps, before they get too far down the road. And particularly when we're looking at the electric aircraft architecture, I'm sure there's not one defined architecture that's going to work today. And therefore, the HIL gives us that ability to try multiple different architectures and test the benefits and the pros and cons for those sort of architectures. Yeah,
exactly. I do agree with you. Chris, do you want to add anything?
For sure. I think it's going to be a significant challenge, but I think there are some cases where this could be done. So I'm thinking for system design, if you've got hardware in a loop models that are very mature from your sensors and things, so they may have been developed and validated based on behavior from other aircraft, I think they can take you a long way with that prototyping. If there's a lot of maturity in those models, that's really going to benefit the system design. So I do see some potential there that actually it's maybe not for the controllers, but the kind of other effectors and sensors that are in the system. You may be able to kind of do your system testing with those models and then jump to the real aircraft. And yeah, so definitely some potential. It challenges really around the kind of processing power needed for that fidelity of the model, and whether you can have a kind of lower level of detail that is satisfactory to fully understand that system.
Yeah.
Well, to answer your question, SOHEIL, about if you can expect HIF especially to replace prototypes. So I mean, I work for OPAL-RT, so we do manufacture test benches. So I would have some interest in saying yes, but in my opinion, the answer would be rather no, or not yet, because in the end, what we want to do with these test benches is to somehow facilitate and to make these design phases and these testing phases as smooth as possible, and if possible, a little bit more cost effective. I'm not quite sure we will someday reach the point at which we are going to replace completely tests and prototypes with hardware in the loop. For sure, we will use less prototypes. So instead of crashing 50 prototypes before first flight, we might need only 5 or 6, because hardware in the loop can help us prevent multiple failures that would have been detected virtually or using all these simulation environments. I don't believe that we would be able to certify any system without having a like real physical proof. It's just like I mean, we have lived this situation during the pandemic, so we have worked a lot from home and making these call conferences. It does not replace like meeting people physically. So there is some extra value to having like physical interaction with people. It's the same when we are dealing with engineering. Obviously, virtual tools can help a lot, but we still need to have prototypes that are real, physical, and that we can see, and that we can observe to check that they are behaving as we expect. So replace prototypes, I would say no, but at least reduce the number of prototypes that we are going to use, which for sure decreases development time and as well cost. So yeah, that would be my word here.
Very interesting. So we have got 5 minutes. I just want to kindly ask, because all the panel members are well-known guys from industry. So I just want to kindly ask them to wrap up the session in 1 minute. It's their expertise. There are lots of questions from audience. I will try to accommodate some of them at the end of the session. Just one of them is a very interesting question for me from an anonymous attendee. Says that, what do you suggest to the students in aerospace regarding HIL simulation? What are things we need to know before learning HIL simulation, and what are the career opportunities? David.
I think the key for me, and I mentioned at the very beginning, is the system architecture. It's to really understand and have the ability to define that system architecture in terms of what the design brief is. Now, of course, on these particular electric aircraft, we're going to have to come up with a design brief ourselves until the authorities catch up. But that is the key, the system architecture. Anybody, a student, try and understand how system architecture works and the whole systems methodology.
Lovely. Andrew.
I think the key is understanding the physics. You've got to pick the right tool for the right job, and you can't do that unless you understand the physics properly. And that's true whether it's numerical simulation for aerodynamics or FEA or hardware in the loop. You've got to understand what's going on so that you make sure that you simulate the right bits and you have the hardware for the right bits, and then you can judge the answer accordingly.
Brilliant. Chris.
Yeah, I'd really encourage the students to kind of get hands-on with the model and start to develop them, but always kind of think about that endpoint. What are they trying to do with the model? What are they trying to achieve? Don't lose sight of that, because you can carry on kind of improving the detail in your model continuously, but yeah, don't lose sight of what you're trying to achieve.
Very interesting. YAHIA.
Yeah, that would be something very, very important to keep in mind. And thank you, Chris, for your comment. Don't forget the objective. Don't forget the requirement. Don't forget why you're doing things. That's the first question I ask people I interact with when they ask me, whatever. My question is, why are we doing this? What is the reason for that? We shall not forget that HIL approach or HIL is just a tool. It's supposed to help us achieve some objectives. It's not the purpose on its own. It's just a tool. So we shall, let's say, evaluate properly what we want to do, where we want to go, and the HIL is just a tool that can help us, or that can make that journey a little bit easier at some point. So I will elaborate a little bit more on this during my presentation. But yeah, basically, we can be confident because there are tools that can help us to design these super exciting new systems.
Many thanks indeed. Perfect. So system architecture, understanding the physics, and don't lose the objective requirements, and don't lose your sight. I think it's more than enough to start for the students. To be honest with you, I'm really enjoying this discussion, and I wish we could continue it for hours. But unfortunately, we have to park here as the time is over for this part of the episode. I hope we can have a chance to have our respected panel members in another episode or event and continue this interesting and fruitful discussion. Moreover, I can see, as I said, there are several questions from the audience. I will try to accommodate at least some of them in the Q&A session at the end of our episode. Once again, thank you so much for your invaluable contribution to this episode, guys. Now, let's listen to YAHIA BOUZID from OPAL-RT. YAHIA, I'm eager to hear more about what you are doing on HIL test benches for advanced and more electric aerospace.
Thank you very much. Yeah, thank you, David, thank you, Chris, Andrew as well. Thank you, SOHEIL, for moderating this session. So I would like to share some, let's say, some insights, some experience with these hard-in-the-loop test benches. So I guess you should be able to see my screen now with these hard-in-the-loop test benches, advanced and more electric aerospace.
Yes.
Great. So it will take about 20 minutes. This will give you, let's say, OPAL-RT's point of view about this exciting topic. I will start with a very brief presentation of the company, what we do at OPAL-RT, then again mention a few challenges related to these aerospace applications. So we have talked about some of them already. So this will just refresh some ideas. And then I would like to talk about the benefits that we see for these HIL test benches and present a couple of projects that have been completed already. And obviously, yeah, if you guys have questions at the end of the presentation, please feel free to write them down on the platform. So OPAL-RT Technologies currently, so we are the world leader in the development of real-time digital simulators. They are based on PC and FPGA technologies, and they are used to design, to validate, to optimize, and to maintain complex control systems. So the what we do is design and manufacture real-time simulators, which are part of the HIL test bench. So they can be very compact things that we can put on the table and that we can use for small experiments, until larger integrated test benches, which include other services such as signal conditioning, such as harnessing, so that we can connect with the device under test. Obviously, behind all this hardware, there is software as well, which represents the physical system that we want to simulate. Can be, you know, the aircraft dynamics, could be the electrical systems, can be the air management system, can be, I mean, whatever system that is supposed to be controlled with a physical controller. Currently, we have 7 offices all around the world, opening a couple more in the next few months. 300 employees, and yeah, almost 1,000 customers today that trust us. And we also count on a network of distributors that represent us locally in different regions of the world. Yeah, so basically we try to be everywhere to help our customers deal with their projects, which are involving complex control systems in different, let's say, engineering, yeah, different engineering projects. So the purpose, generally speaking, of these HIL test benches, so you guys already understood that, we are talking about testing control systems. So we want to facilitate the design of algorithms, we want to debug these algorithms, we want to validate the final controllers once they are, I mean, almost ready to mount on an aircraft. We can simulate flight dynamics, we can assess safety, we can deal about these topics about UAVs. We can introduce the e-mobility topic that is very hot these days. And very trendy topic as well is the MEA and whatever onboard power systems we can have on the aircrafts. And this is a big topic of research today, because there are many constraints related to aerospace that we don't have on ground systems, such as, I mean, a car or on a land power system. So we have to talk about efficiency, we have to talk about power density, EMI. That can be a very big topic that has to be covered as well. So even if we do have experience from automotive, for example, or even if we do have experience from, let's say, power systems, I mean, traditional power systems that we can have, well, the constraints are really different, and these constraints can really change completely the paradigm. So we have to take them into account. So if I try to sum up some challenges, of course, not all of them, but just some very general challenges. First one is the complexity of the systems we're talking about. They can be extremely complex. So today, if you take a commercial aircraft, I mean, depending on the size, you can have between 200,000 and more than 3 million parts, like mechanical parts. If we speak about the smart part of it, so the control, the embedded control, we have, I mean, we're talking about millions of lines of code, and this number is going to grow a lot in the next decades. So if we take, yeah, so a Boeing 787, we evaluate the let's say the volume code that is embedded to 12 million lines of code, which is huge. Even though in automotive they're not that bad, a high-end car today can have up to 100 million lines of code. But still, all these things have to be validated, and we need to make sure that the software is working properly, it's doing the right thing, and we don't have a bug that is going to cause some catastrophic event. Second thing is that we need to validate as many things as we can before the first flight. We don't want to crash a prototype. We don't want to hurt people. So we have to test these complex systems, so these aircrafts in nominal conditions, but as well in faulty conditions. That's especially true as well if we consider that we cannot reproduce, let's say in real life, some of the faulty conditions. If I was supposed to validate some functions in an aircraft, and if one of the tests was okay, just cut all the wires and see what happens, I mean, I wouldn't like to be on board at that moment. So these kind of things could be tested on the ground using an HIL test bench, for example. We need to test the interaction between systems, because this is a very tricky thing. You can have systems that are just working properly when they are in standalone mode. But as soon as you connect them with op systems, then you start seeing strange stuff happening. So integration tests are super important, because when you put things together, this is when you start seeing problems. And the test combination can be countless, not only because we can have a very huge set of inputs, but as well interactions. So you are just multiplying things together, and it can grow very, very fast. As well, something that we have to keep in mind is, well, the tests that we can perform on prototypes are limited. So we can't do anything on prototypes, and we can't build as many prototypes as we want, because they can be super expensive. So Iron Birds, or like physical prototypes, I mean, they have a high cost. They're not super flexible. It takes a long time to build them, to configure them, or to modify them. If we rely only on this kind of, let's say, testing systems, well, we would need to wait a lot to have them available. But we want to start testing stuff as early as possible, because the earliest the better, the best, sorry. And last thing I wanted to, almost last thing is the new challenges that are brought by electrification. So it's, even though it's a topic that is pretty well known in other industry domains, it's somehow kind of new in aerospace, because we need to validate generation, storage, and distribution systems which are on board. We have all these constraints about about the weight, about the size, about the vibrations, about EMI, about safety. So we have an increasing power demand that is on board due to all the appliances that we want to put inside the aircrafts. We are putting more and more power electronic devices, which can generate EMI, of course, and we need to take care of that. What is the impact of this EMI? So we need to make sure that our systems are reliable, that the power quality is good, and that we are not somehow creating conditions that would lead us to a unwanted behavior. Yeah. And then we have the question of the maintenance. So the life cycle of an aircraft can be very, very long. So it's not 5 years or 10 years as a car. It can be 50 years, sometimes more. So we need to keep let's say, the system well maintained, and what are the tools that can be used at that point. So how can we make sure that we can properly design and let's say commission systems, but as well maintain them during decades. So these are the problems that we have to face, or at least some of them. Now, how can we tackle some of these issues thanks to HIL test benches? Well, in a few words, and I mean, if I had to sum up the whole thing in one single slide, it would be this one. The benefits of HIL test benches are that we can, I mean, the availability is key. We can reconfigure systems. We can replace hardware by software models. So we can somehow modify the system, or we can adapt it in a very easy way because it's software. We have the safety topic. So there are, I mean, either because we are talking about power systems which are driving power signals, or we have moving parts, or we have dangerous test cases. So all these things can be tested on the ground and can be tested on virtual models. We can have as well a very positive impact on delay. So we can execute these test cases on these virtual models using real-time or accelerated simulation. We can automate all these tests, and we can validate progressively all these complex control systems. In terms of feasibility, so there would be tests that we wouldn't be able to do, I mean, in real conditions, especially these dysfunctional or extreme cases that we can do very easily using a test bench. And then the cost, obviously. So because we are not, let's say, crashing too many prototypes, or because we can use the system, or because we can detect very early mistakes in the software, well, that has, I mean, a significant impact on the cost. So in the end, just to sum up things, if we make earlier tests, if we use less prototypes, if we can make safer tests on the ground, and if we can be a little bit more exhaustive, for sure, this will help the program to work in a smoother way. So in terms of modeling, that's a very important part, because somehow it's the core of these HI test benches. So we can model, I mean, almost any kind of thing, just a question of what is the level of detail I need, and what is the expectation, and how far shall I go in the modeling. But we can model mechanical systems, hydraulic systems, electrical dynamics control. I mean, whatever thing you have in the aircraft could be modeled at some point. There are specific tools for very detailed models. So we covered this thermal topic, or we have IFEA analysis as well that can be done offline. Then we have the real-time part that deals more with the with the dynamic behavior of the system that can be done in real time on a HI test bench. This can be used for, I mean, proof of concept of very preliminary design, so we can start seeing things and we can start designing in a proper way our systems, even if we don't have anything physical sitting in the lab. So we just have computers, and we just want to see, okay, this is what it would look like if we wanted to go I mean, to the next step. If you want to go a little bit further, we can start integrating physical devices. It could be, sensors, actuators, control systems. So we can have this kind of hybrid setup where we have part of the system that is simulated and part of it that is real. And this would be one of the pictures related to HIL. We have the control prototyping as well that would be part of this, of this concept. But here we want to go the extra mile. That is, okay, virtually speaking, everything works. Now I would like to see what happens if I try to go a little bit closer to reality. So I start integrating physical devices and see how they interact with the virtual part of the system, which is not physically usable at that point. So these HI test benches, so they can, there can be a different test bench for every single project, but basically you can see them as big racks like this, where you have a computational part that is taking care of the simulation. You have some hardware devices that allow either to emulate signals, or to connect control systems, or to adapt signals. So what we want to do here is to emulate an environment that would somehow behave as the aircraft or a subsystem of the aircraft. And obviously behind the scenes, we still have these models running that are really giving the behavior, and that is being then translated into input-output signals that we talk with the, let's say, with the control system. And as I mentioned before during the panel discussion, is that well, these HIL test benches, this simulation approach, can be used obviously during very early stages of a project, during proof of concept. That's fine, but not only there. So we can use it a little bit further during design. So once we need to go more into details and we start really writing algorithms that would control whatever subsystem of our aircraft, we can use them for validation. So once we have a prototype of a control system that would be almost ready to be installed on an aircraft, well, we can test it with a HI test bench before. So this helps a lot to debug and to make sure that the integration of software and hardware, like the microcontroller, has worked properly. And once the aircraft is flying, well, we can still use HI test benches for the maintenance. So either to update the software and test these updates on the ground in the lab before uploading the code in the aircraft, or in case we need to reproduce some behavior that has been observed. So we want to run test sequences or whatever condition has been observed, which led to some behavior of interest. So that can be reproduced as well using an HI test bench very easily and many different times. So just to give you a few examples here. So in terms of, I mean, the first step that would be the proof of concept, we had this project that was, well, that was 15 years ago already, with this customer saying, okay, I would like to simulate a complete onboard power system. And the issue is that to run one test scenario, like just for one run, that took 90 days because the model was so complex and it took so much time to compute that they needed, like 3 months just for one test case. So that would have made impossible to meet the deadlines. So they came to us saying, "Do you guys have some solution for that?" So we did. So we somehow used one of our simulators to run their model. Then we split them into different cores, we made some parallel computation and stuff. And in the end, we ended up with a decrease in simulation time down to 24 hours. So it was almost a factor of 100 in terms of acceleration. And thanks to that, they were able to move forward with their project and meet somehow the deadlines. At least it made the project feasible at some point because they were about to abandon the project at the very beginning. If we talk about the next step, that will be the design. Well, we can use this real-time simulation and these HIL test benches, well, to design new control algorithms, especially if we have already existing actuators and sensors, but we just want to improve the control part. So we want to try some new algorithmic approach. So the issue here would be to develop new control systems on existing plant systems, but we don't have time to, to design the complete hardware of the controller. We don't have a software team that is capable to generate code for that. So we just want to focus on the algorithm part. So only the, really the smart part without needing to take care of, okay, who's the software guy and who's the hardware guy. So we just want to make sure that a new control strategy is going to work better on an existing set of sensors actuators. So here we can use the test bench as a control system. So we can implement control models inside, and the HIL hardware would work as the control system. So we can have this control as a virtual model that will be driving a physical set of actuators. In terms of validation here, that would be like a further step, meaning, okay, I have my software, I have a hardware team that has developed the PCB with the microcontroller and the memory and the IOs and all that stuff. This software has been embedded in the microcontroller, and I want to check that this thing is working properly before first flight. So this would be the issue. I want to validate the final control system, so it's ready to mount on the aircraft, but I still want to see what happens in the lab before going real. This would make sense, especially if the controlled system, if the plant subsystem is not available, or if we don't want to do the tests, in real life. And then the test bench can be used to simulate the aircraft subsystem or the complete aircraft. And then we are going to connect the real physical control system that is under test and check how it is behaving under different conditions that we can emulate as well in the HI test bench. Then last but not least, for the maintenance, the idea is to be able to develop and validate updates for embedded software to reproduce issues. So this was mentioned before. The HI test bench can do that. So it would be used as a replica of the aircraft, and the aircraft subsystems or the complete aircraft would be the virtual model. So in the last minutes I have here, just want to mention a couple of projects that we have been involved in the past few years. So we have delivered a few test benches already for Libya, that is a key company that is developing embedded air management systems, and they are using our test benches to validate their real controllers, and they are simulating the complete air system that is inside a commercial aircraft. And this allows to run multiple projects in parallel. So they have one test bench for every single project that they have. So they can run multiple different tests at the same time, and they don't need to use all the time the real physical prototype of the air system that has, you know, all these compressors and all the pipes and all these electrical machines. This is simulated, so it goes much faster. And then they make a couple of final tests on their physical prototype before they deliver to the end customer. One very nice success story we have is with MagniX. That is a company that is, let's say, developing motors for, propulsion systems for aircraft based on electrical motors. And they were able recently to equip a couple of small aircrafts with these electrical propulsion systems. So the whole electrical part was simulated in the OPAL-RT system, and then they wanted to test the real physical control system. So the results is that they were able to equip a seaplane that they call the E-Beaver, and then a Cessna that they call the E-Caravan with full electrical propulsion. So today these prototypes are flying. It's working not that bad, and this was performed back in 2020. What they measured as well is the power cost for a 30-minute flight, especially for the seaplane. And they told us that the cost was about $8 with the full electric propulsion, whereas it was $135 with the traditional fuel-based propulsion. We have as well this research institute in Toulouse, IRT, that are making a lot of tests here in the more electric aircraft project to assess, let's say, electrical drives. So they want to test and they want to measure how a set of converters and machines, electrical machines, are working on the ground, but they want to assess especially the, not only the electrical behavior, but as well the EMI behavior and thermal behavior. And this is part of the research projects that are ongoing, these times here in Toulouse for this future MEA project. And well, last but not least, this is a nice benchmark that we did a couple of years ago for Boeing, where they wanted to study or make a proof of concept about an embedded power system, an onboard power system composed of multiple generators, of a bunch of loads, and a complete power system with different, electrical buses, with different breakers, different points, with all this redundancy as well implemented electrically speaking, with all these conversion units, with all the storage. And they wanted to see, or have a first idea about how this complete system would behave and what would be the right architecture to implement. So we ran certain simulations with them to make sure that the validity of the models were good, and that is somehow the starting point for them to start the architecture design. So as a conclusion, well, we have said this thing many times, and all you guys are aware of this. Aerospace systems are really challenging for many different reasons. Two of them is that controls are getting more complex, and because the systems are getting more electrical, and this is kind of new. But the good thing is that there are tools that can help engineers to design properly and to test these systems. They facilitate somehow the design, the validation, and as well the maintenance. So don't lose hope. There are solutions. We are engineers, and we know that whenever you have a problem, you have a solution as well. So thank you very much for your attention, and maybe we can move forward with the Q&A session.
Thank you very much, Yahya. I really enjoyed the talk you delivered, and I'm really excited about what you said and the projects that you described. So I have lots of questions personally, but let's give the priority to the panel members and the audience. Is there any question from the panel members? So lovely. Let me select some questions respect to the timeline from the attendees. One question specifically to you, Yahya, is from an attendee, says that, does AMESIM software, I think it means SimCenter AMESIM, the software by Siemens, does AMESIM software work with OPAL-RT via co-simulation environment?
So the answer is it works under certain conditions. So we do have a few projects running with AMESIM models that are embedded inside the OPAL-RT systems. Actually, the main topic to cover when doing this, and the reason why I don't say 100% yes, is because the AMESIM is an offline tool. So the solvers which are used are not meant to be real-time. So sometimes we will need to tweak a little bit the models to make them real-time compatible. But in principle, that should be fine. And by the way, if you are using AMESIM, you should have the option where you can generate code for OPAL-RT systems. So that's like by default there. But then to make it really work, we just sometimes need to tweak a little bit the model to make sure it's real-time compatible.
Yeah, perfect. A question from my side. I have tried to accommodate some points from the attendees as well. Can you tell us very briefly about the hardware that you are using or you prefer to use for the HIL? Of course, it depends on the model and system and the level of the project. But can you tell us about the hardware, the automation technique that are used in the generation of the test cases in the HIL systems?
Well, actually, there are different levels. So in terms of hardware, the systems that we manufacture, they are based on, let's say, on powerful computers. So it's computer CPU-based systems with FPGAs to deal with the I/O management, which are super fast. We use the FPGAs as well, which are very fast units to simulate the electrical part, especially the power electronics. So we are capable today to run rather complex converter, sets of converters with time set below a microsecond, which allows for tens or sometimes hundreds of kilohertz of switching. That is really cool. So that would be more in the system modeling. Then we have the test cases or the test automation, which is a different layer. That would be something that is above, which is more based on the, let's say, the system, on the functional description of the system and what it's supposed to do, which is not primarily what we do at OPAL-RT. So we focus a lot on the simulation of systems and making sure that we have a real-time closed-loop behavior. But then on top of that, our users, they can develop their own test campaigns to make sure that they're covering the features that they need to validate.
Perfect, many thanks. So maybe the last question from respect to our time, the question from Swat. She has a very specific question, that a short question regarding the point you mentioned about building a resilient system and taking into consideration the unexpected behavior. And you said something, Yahya, about the failure modes and something like that in your presentation. In terms of control, it is the FTC, fault tolerant control strategy. The question is that, did you ever consider the ATC, attack tolerant control, or cybersecurity into the HIL process?
Wow, okay, that's a tough one.
Yeah, yeah, maybe an opening for future discussions. Yeah, it's a very, very interesting question. I personally don't have any experience on that, but if you or any other panel members have any thoughts, I would be very interested to hear.
Yeah, to be honest, I'm not a cybersecurity expert, but actually, what we know and what we see from from some of our users is that the cybersecurity topics are being more and more addressed now, and there is a need for that because I mean, it's nice to see if the system is working properly or not. Let's say if it's just, I mean, if you just leave it alone and leave it work as it should. But then if you are trying to interact with it in a, let's say in an evil way, that's a different set of inputs that you are trying to set there. So for sure, there are initiatives now aiming at studying what would be the, let's say, the consequences of cyber attacks on different systems. So we do have this request more on, let's say, based on power systems, which are ground power systems, which would possibly apply as well on board power systems. But this is still I mean, I don't have much experience on it, and I know that it's a kind of trendy topic of research right now because the causes are different, even though they might impact the system in similar ways. But we still have to take care about what is the cause, what is the origin, where does it come from, and this would definitely be something that would be unexpected. So how the attack would happen, where would it happen, and how many systems would be attacked at the same time.
Brilliant. Yeah. Thank you so much, Yahya, and thanks, Suad, for your interesting questions. Any other views or comments from the panel member on this question?
Yeah, I'd like to comment on that. And yeah, it is going to be a significant challenge, the kind of cybersecurity in our industry. And it's actually dealt with a similar way to how we deal with the safety. So yes, we have to design in the cybersecurity protection, and that results in functionality. So then we have to test, validate, verify that functionality. So it starts with an assessment of what those threats may be, and then on our benches, we are then verifying that that is actually protecting, that function is protecting us from that threat.
Yeah, perfect. Many thanks indeed, Chris. You can imagine that there are many more questions from the attendees, but unfortunately the time is over and we have to close the session here. Some of the questions are answered by the panel members in the chat box. Thanks, Chris, for that. But I do apologize that we don't have enough time to cover all questions here. Maybe, hopefully in the future, we can have more episodes and webinars to discuss this interesting and challenging topics with more details. Again, a special thanks to OPAL-RT for sponsoring this episode, and many thanks indeed the respected panel members: YAHIA BOUZID, Technical Director of OPAL-RT Europe; David Shaw, Non-Executive Director from Britten-Norman; Chris Leslie, Digital System Engineer from Vertical Aerospace; and Andrew Raw, UK Chief Engineer from Ampaire. And on behalf of Foresight Aerospace, I do appreciate the attendees for your time and interest and interesting and active contribution to this session. Hopefully we can see you in our next episodes. Have a lovely day and bye.